Okay, come back everyone. So in this tutorial session, I don't have any sort of specific questions. I don't have any exercises. I don't have any of that to give you. What I wanted to do is to just use this time to just have some discussions, okay? So back home, every Friday evening, we have a group meeting, and then we go and have a beer. And usually over beer, we just end up talking physics and talking about what things mean. And so I'd like to try and sort of recreate a bit of that here and just go over some of the concepts that we've been looking at yesterday, today. We'll see more tomorrow. And if then we have other time, I've got other slides, things that I can show you. So for example, I didn't complete, show you everything that I wanted to show you yesterday. So I sent out two files. One was Hawking's original Nature paper. I guess we could start from there. That's probably going to be the shortest topic. I just wanted to sort of go over together, you know, starting from what we saw, especially yesterday. Remember, I sort of gave a general overview of how people often usually approach sort of the calculations and understanding how a time dependence, for example, in a quantum field theory gives rise to particle production, okay? And I gave a whole list of examples and situations where something like this can happen. So the example I was looking at yesterday was an expanding universe, so our refractive index for an optical material is just all our metrics was only a pure function of time. Today, we looked at a more complicated case where it's a function of z minus vt, and you can, as I mentioned, you can then just build all the kind of analogs that you want and look at various different kinds of phenomena. So I wanted, with that in mind, I wanted to go through the exercise together of trying to identify those key elements, okay? So the key elements were the time dependence. The other key element was then finding final states, output states, as a function, writing them as a function of the input states, and then looking for these Bogel-Lyubov coefficients, and then from there calculating the number of generated photons. Okay, so this is sort of the steps that one goes through. So, and that's true for any physical system. And so what I'm hoping is that with that background, even if one doesn't understand all of the theory, all the calculations in the paper, can one quickly identify exactly what's going on and follow the line of thought. And then the question is everything correct as it should be, or is there anything unexpected in there? Okay. So first question, has everybody actually read this paper? So these are yeses, people putting their hands up. Okay. So some people haven't. Okay. So let's maybe just go through it together. I don't want to read all of it because I don't think that would be a very good exercise. But, okay, how can we do this? Let's see. Maybe I've already highlighted some sections here for you. I'll just read through the highlighted sections, then we can discuss maybe together what they actually mean. So here, for example, there's a sentence where, so the first part of the paper is just giving an overview of the main findings. He's saying that he's explaining how he's gone through the calculations and discovered that a black hole will give rise to photon emission, and that this is in the form of a black body, and the temperature depends on the mass. So as it evaporates, the mass becomes smaller, the temperature becomes higher, and so on. So you have this runaway effect. Okay? And now he's starting, so to see how this thermal emission arises, so I start to describe in detail how to look at this. Okay? He starts from a massless, so he's talking about he's talking about photons, massless scalar field, which obeys some wave equation. Okay? Remember, we said that the key element was you've got your input field, and you need a wave equation to propagate that through. Okay? That contains the metric, of course. So don't worry too much about how that's written. Okay? It's some weird notation that he's using, but it's a wave equation. And that's sort of one of the key things. In an asymptotically flat space-time containing a star which collapses to produce a black hole. Okay, so what elements already in that sentence do we have in there that sort of refer back to what we were talking about yesterday that we can identify? Asymptotically flat, exactly. So yesterday we were talking about the fact that you have to take, I was drawing sort of a potential which is like this. So I was just referring to some general v of t, and I was saying at t equals minus infinity, you want this thing to be flat. And equally at t plus infinity, I want this thing to be flat, okay? So that asymptotically flat means the space and time very far away from the black hole, we're flat. Good? What else do you see in there? The crucial ingredients that we needed. So yes, well, yes, that's not what I was looking for, but yes, there's an operator there, or there's our propagation field, but it's something else that I was looking for. Okay, so we need something, we need a potential, something that depends on time. What is that in this paper? What would you identify that to be? I mean, I guess the question is, if you want me to be formulated differently, is the picture we have of a black hole. So if you think of a black hole, I'll ask a more explicit question. Where's the time variation? This is actually what I really want to talk about right now. Could be. In what sense? Let's maybe come back. Let's hold on to that thought and come back to that later. But there's a word in there which implicitly implies that there's a time variation. Sorry? No? No? We're talking about the physical system. You've nearly used all the words up there. There aren't that many left. Collapsing, yes, collapsing. He's talking about a flat space-time containing a star which collapses. Okay, we went by elimination there. There weren't any other words there. So this is precisely the point. So so what are we simulating? This is the question, right? We are simulating. So when you say we, so my question is, what is he simulating? Okay, that's not what he's saying. Okay, this is why we're going through this exercise, to see what he's saying. And then we can go over together, very hand-wavingly again, I'm not a theoretician, but we can hand-wavingly go over how people do the calculation, so the more modern version of this calculation. But if you look at what he's saying, he's talking about a collapsing star. Okay, so often you see these sort of graphs where you have time on this axis, and people sort of draw this is the shape of the radius of your star, and it collapses inwards. Okay, and then reaches the singularity. As it collapses inwards, sort of the horizon moves outwards like this. Okay, and so there's this dynamical process which is evolving over time, and if we're to read what he's saying there, asymptotically the space-time is flat, but it's containing a star which collapses to produce a black hole. And I think further on, let me see, I think there's something more. There you go. Look at this sentence here. It says the beta, okay, and he's using the same letters as us, the same Greek letter, the beta coefficient there, will not be 0 because of the time dependence of the metric during the collapse. Okay? So he's looking at this. You know, he's coming from this school of thought where it's sort of what I introduced and explained yesterday. Okay? You have this time variation, then you're asking yourself, so something, you have asymptotically flat, then you have something that shakes things up in time during a certain period, and then it goes flat again, and you're comparing the output to the input, and you notice there's a difference. And this is how you sort of set out to do that calculation. So the beta will not be 0 because the time dependence of the metric during the collapse will cause a certain amount of mixing of positive and negative frequencies. This sentence summarizes everything we went through, sort of the whole of yesterday's lecture. Okay? And that's what he's looking at. And if you want to sort of apply that way of thinking without too much sort of remodulation of the process, then you're kind of forced to go and look at this the dynamical process where things are collapsing. Okay, so I mean, it's kind of highlighted. Let's come back to this in a second. I just wanted to still finish the exercise of, so what is the very last thing that you can identify? You can see it's already highlighted there. That's the key component to then actually pulling out the fact that we have particle production. And it's kind of already highlighted. Okay, so I'm essentially just pointing out that the photon number that you generate at the output is given by this beta squared. Okay, so all the elements are there. You don't need to, you cannot understand all sort of the details of what's going on. Just by looking at sort of the key elements, you can identify one-to-one identification in this paper. What we saw yesterday, maybe it's worth just looking at how the calculation does continue. I mean, essentially what he's doing here, this parts of this column here is essentially going through sort of the details, a little bit like when I showed earlier today, when I was showing that you could, for example, use applied WKB approximation to solve the wave equation and pull out sort of the logarithmic divergence and all these kind of things, okay? He's not doing the same thing, he's doing something similar here. He's trying to sort of build an analytical approach, finding what the solutions look like to his wave equation in the presence of this Schwarzschild function, okay? And then moving on, if you look here, what he finds at the output, he actually finds a relation between the alpha coefficients and the beta coefficients, okay? And what he's writing is that his beta coefficient divided by the alpha coefficient is given by some negative exponential. What letters is he using? So it's got pi omega divided by kappa, surface gravity. Okay? So that's the relation he pulls out between beta and alpha. But remember, so what's the other relation? So this is what then leads me to conclude, or led Hawking, to conclude that he had the black body dependence. Do you remember we found another relation for alpha and beta? Do you remember what that was? Exactly, okay? So I can take this, okay? And I think he does, I'm sure he writes it somewhere. Must be there. It is there somewhere, I think further up. But this is also in his paper, okay? So you've got two equations, two parameters, you can solve that, okay? And if you do, what you find is that your beta squared is given by, well, that's not how he writes it, actually. It's pi omega kappa minus 1, okay? It's exactly what you've got. There you go. It's written here. Okay, so that's where this, so if you're reading through this and you find this a bit mysterious, all he's done is he's plugged that relation into the alpha squared minus beta squared equals 1. And so your photon number is 1 over this e to the pi omega divided k minus 1. Okay, now if you notice, again, so this is coming back to what I was saying earlier on, there's no h bar in there. Okay? Common wording that you'll find is that something, an effect is quantum if there's an h bar in the formula, or yeah, so if the h bar appears, or alternatively, if you send the h bar to 0, does the effect disappear or not? Okay? That's what allows us to distinguish whether something's quantum. And there's no h bar in there. And the h bar comes in, this is next sentence. Let's see, where's this? There you go. Saying, but this, he's referring to that, but this is just the relation between absorption and emission cross-sections that one would expect from a body with a temperature in geometric units of k over 2 pi. That's where the h bar comes in. he's comparing, he's saying that formula there is just identical to this formula. Okay, so question, although I did sort of hint at this yesterday, is Hawking radiation a quantum effect or not? So what are your thoughts on the basis of what I just did? Right, true, yeah. So just by equating this to this, actually this is how you pull out the temperature. So today I gave a very sort of like very hand-waving derivation of the temperature. And someone was asking me questions about, you know, I could have chosen a different function for the Schwarzschild radius. Why did I just take RS? True, but the point was that that wasn't the proper way of deriving the temperature. This is the proper way of deriving the temperature. You're right. I say this is equal to this, then I can write T equals, and I can pull out my Hawking radiation temperature. But this is precisely the point, and that temperature will have H bar. But where does the H bar, I mean, think where the H bars come from. I mean, is it part of the derivation? Is it part of the actual physics through which the beta is created and is therefore greater than 0? Or is it something that I sort of slipped in at the end? And if so, and does that make the process quantum or does it not? The delta E equals KT is not, that's still classical thermodynamics, right? True, yeah. That could be one way of saying that he was using, and he does use creation and annihilation operators. But I mean, remember yesterday when I derived this, I didn't actually use creation and annihilation operators ever. So I could argue, yes, in this paper he gets there using A and A daggers or B and B daggers, whatever. But you can also get here without using A and A daggers. Yes, I don't think he ever, I don't think there's ever even a need to sort of pull the Born rule sort of into being. And you're never dealing, and if you're dealing with photons, and strictly speaking here, you're not talking about, you know, how that measurement or Oh, sure. In that sense, yes. Yeah, sure. Okay. Yes, that's. I mean, I'm not saying there's not a right or wrong answer here, by the way. This is just a discussion about whether one should consider the physical process. So this is the question. It's not the final formulas of quantum. I'm not sure. It's got an H bar, but it's really about the physical process. So with which a black hole amplifies the vacuum fluctuations. And if I truncate that, so if I say that sentence as a whole, of course it's quantum, because we're talking about vacuum fluctuations. But let me truncate the sentence. Is the physical process by which a black hole amplifies classical or quantum? Yes. No, so you're talking about, this is the surface gravity, and this is the Boltzmann constant. Here, this again that's the surface gravity. It's this kappa here, okay? But it's really about, you know, how you define whether something is quantum or not. Are you happy? Because if I was to stop the derivation here, okay, and I look at the final result, you know, yesterday I derived this. I never used H bar. I never used creation and annihilation operators. And then I've got this formula, and it still doesn't have an H bar in it. How do I know there's anything quantum there? So is that true? Does everybody agree? I mean, it might be true. I mean, is it true that you can have quantum effects where H bar never appears? Sorry? For example? I don't know. I mean, it's hypothetical what you're saying. It could be, but I think if you actually try to come up with an example of something. I'm not sure I would agree with that. Okay, so I'll send out another paper this evening by Landau, okay, where he sets out to build, I can't remember the title of the paper, but it's something like building a physical theory for units of measurement. That's his starting point. So he's saying rather than trying to build a system of units, well, let's replace the international system of units, for example. So how would you go about that? Saying, well, rather than starting from the meter and let's, from how big is this, how much does this weigh, let's start from physical theories. And what he comes up with is that essentially there are only a few constants that count, okay? And here's the sort of the concepts in that book, in that paper, sorry, were then sort of summarized in a book by a French science writer. I can't remember his name offhand. He comes up with this cube of theories, okay? So on this axis, I can put G. On this axis, I can put HR. And on this axis, I can put V over C. And Landau, essentially, in that book is saying that's all you need to know. So, and then he's build a cube. See if I can draw a cube here. Okay, I can draw a cube here, and essentially by identifying where I am on that cube, I can identify any given physical theory, so the area in which this physical theory sits. So for example, if I'm here, this is what I would just call classical mechanics. Nothing quantum, there's nothing relativistic, there's no gravity involved. Okay? Then as I move up here, for example, I move to sort of general relativity. Okay? That's the idea. If I move along here, I become quantum. And if I move along here, I have special relativity. Okay? And you can go and look, for example, at all the intersections that you have here. So here, for example, you'll have a relativistic version of the Schrödinger equation. Okay? So relativistic quantum mechanics. If you're up here, you'll have, this is sort of like the big open question in all physical, sort of big open questions. So it's their physical theory here, where you have quantum. So you're combining here gravity with special relativity. So that's general relativity over here. So if I then also add quantum, I'm asking myself, is there a quantum version of the Einstein equations? Okay, but so then I'll finish if you let you speak. So his point being that quantum is indeed identified by the presence of an H bar. Mm-hmm. Mm-hmm. Yeah, yeah, yeah. On anything. I mean, I guess, for example, you'd say that if you have an equation, so you've derived, you've built yourself a theory of some kind describing some physical situation. I mean, you can take it at any point, but... Sorry? So, I mean, the point is, for example, I mean, if we start, let's have a look at, for example, this axis. If I have an equation and I send v to 0, and the effect that I'm looking at disappears, well, then I would claim that that was what I was looking at was a relativistic effect. Okay, and so that's sort of the reasoning here. And likewise, if I have an equation, I send big G to 0, and for example, take Newton's gravitational law. If you send big G to 0, it disappears. So surely that's a gravitational effect. I mean, it's trivial, right? This is, you find that this is obvious. And likewise here, if I have a formula and I send that h bar to 0, then, and the effect disappears, then that was a quantum effect. So for example, if I'm describing what the energy level is in a quantized oscillator, that's characterized by an h bar. I have to have h bar in there. If my h bar goes to 0 and I lose all of a sudden, you know, my formulas were predicting that my harmonic oscillator is quantized. Now I send h bar to 0, it's no longer quantized. Well then, so, you know, the physics have changed, and therefore what I was looking at before was indeed quantum. Yeah? No, absolutely not. Everybody should make comments. I don't have answers here. I'm just trying to discuss. Mm-hmm. Mm-hmm. Right. Uh-huh. Oh. You mean you want to go through the derivation again, or
no, just one line.
One line. There you go. Yeah. Please do a bigger piece. Yeah. Sorry. You want me to? Oh, you want? Okay. Yeah. You want this bit further up? This one? Uh-huh. Okay, let's pull that down so we can read it properly. Okay, so where are we? In the early universe, yes. No, he's not talking necessarily about that. What he's saying is that how do you form a black hole? Okay, so now we seem pretty certain that all black holes, or most black holes, are formed as a result of sort of the natural evolution of solar dynamics, or stellar dynamics. Okay, so a very large star, very large mass, at the end of its life will collapse in on itself and create a black hole. But and if you go through those numbers and then pull out what the temperature is, it's, you know, you get these nanokelvins. But what he's saying is it could be possible that in the early universe, just due to dishomogeneities, these fluctuations aren't meant as quantum fluctuations necessarily. He's talking about fluctuations in the density, and if they were locally large enough, then those could have created a black hole starting from something that wasn't necessarily a supermassive star, for example. Okay, so that's not a quantum fluctuation. So okay, yeah. Mm-hmm. So you put that here. Yep. Yep. Uh-huh. Yep. Yep. Mm-hmm. So you're saying there's an H bar in there, which came in all the way over here. Mm-hmm. Mm-hmm. Yeah. Yep. Okay, but I would still argue, so I agree, your conclusion therefore would be because the H bar came in all the way at the beginning and survived, I've got a formula here where if I put H bar to 0, the temperature disappears, hence it's a quantum effect. I agree. However, I would also argue that the H bar here came into play because I used the Heisenberg uncertainty principle, so that, of course that's where the H bar comes in. But it's saying, so what that means though is that what I'm looking at here is how a quantum fluctuation behaves. And that's fine, and I absolutely agree with that. So if you look at how a quantum fluctuation behaves in the presence of a black hole, of course you end up with a formula which is quantum, has an H bar, it's a quantum effect. But there's the question I'm asking is subtly different. It's about the physics of the underlying mechanism that leads to this amplification. Is that a quantum effect? Because this is the temperature that I expect to see when I'm amplifying quantum fluctuations, and that has to be quantum. And if there wasn't an H bar, then we'd be in trouble. Something would have gone wrong. But so let's assume, let's think of, and this will be connected to the next set of questions, and I'll pull up another article. Let's think of the experiments that Silke Reinfeldt and Bangalore did. They're using water, okay? And they're sending in, remember they're showing how they had this paddle just moving and sending in waves. Nothing quantum there. Yet, they still saw amplification. So what does that tell us? Is that H bar really needed in there? So if I can do it with water waves. For quantum fluctuation. So if you're starting, from there, you're inputting quantum at the beginning, and you're not really addressing what the physical process is. So I can tell you what my personal opinion is, that this actually is not, the physics behind this actually is not quantum at all. This is just an amplifier. And sure, it can amplify quantum fluctuations. This is something, the fact that you have an amplifier, you shouldn't take for granted that it's just going to amplify anything. It's also going to amplify quantum fluctuations. You need to verify that. Indeed, Hawking did this. But that kind of derivation sort of hides this. But if you go through that derivation and you realize you don't make that very last step at the end and you just stick with the first part of the formula, then Bill Unruh's claim that he's measured Hawking radiation in a flowing body of water, which is purely classical, I would say is, let me rephrase that, it's correct if you rephrase it. It's correct if you say that he has measured the underlying physical mechanism that is responsible for Hawking. Yeah, then there's space. Okay. Okay. So why would you say that's an interesting point. So why would you say that in the gravitational context? So let's say I have my black hole, okay, and now I send in a wave. So you're saying that if I look at what comes out, this will not be amplified. Okay. In a black hole, you're right, I would need a white hole. If I had a white hole, I could do this. I could send something in and then have some and look at the scattering. Let's just assume I had a white hole, right? And we're just talking. So, but the point is you're saying there would be no, physically there would be no amplification process there for classical waves. Okay, I think I disagree with that, based simply on the fact that those formulas only introduce an H bar at the very end because he says, oh, this looks like a black body. And then, Yes. Well, any derivation. I mean, there might be derivations out there where the H bar is just sort of... No. And also in the analog models. So also in our derivations, you know, I mentioned this PRD paper by Belgiorno and co-workers. They go through the whole derivation, and you end up with a formula that doesn't have H bar in it. It's only then you say, oh, that looks like a black body formula, and then you say, okay, let's say it is equal to black body formula. And then you just rewrite you're essentially rewriting the constants and see if you get an H bar. Some questions there? Mm-hmm. Yes. Mm-hmm. Yes. Yeah. 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 But it's a good question. I mean, essentially, you know where you want to get to it. But, I mean, again, let me underline, this isn't the proper way of doing it. It's just sort of a hand-waving argument, showing that you can pull in various constants and glue them together and get something that looks good. So assuming you have lots of photons with an average temperature, yeah? Yes, exactly. Mhm. The radiation comes, so let's phrase that carefully again, but you said it correctly. The radiation comes from the vacuum fluctuations and everything that you just said. I'm talking about where does the physics of the amplification slightly different. Okay, so there's another quick thing I want to discuss about this derivation before moving on to the next topic. And it's related to, you know, we pointed out that Hawking is explicitly talking about a collapse. He's talking about a time dependence which is encompassed in this sort of star collapsing in on itself, creating a singularity, and then becoming a black hole. And there's an obvious time dependence. Okay? But then we also saw this picture is actually promoted by Hawking himself, where it was one of you guys pointed out that actually the picture most people have in mind when talking about Hawking radiation is that you have this static, so this eternal black hole. It's just sitting there, and then you have these pairs of photons or quantum fluctuations close to the horizon. One of the pair gets sucked in, and one escapes. Okay, so you're not dealing with this anymore. Essentially, you're saying that you're over here, so this sort of tails off and becomes flat. This is the event horizon, and you're saying that sort of, you know, you're generating particles are coming out like this. So I know nothing about this. I'm assuming this sort of never happened. I'm just looking at this area. Okay, so how does that picture, now this picture that I was showing here and that Hawking's talking about marries very well with what I was talking about yesterday, where I said the key ingredients are asymptotically flat, so you can write your modes as plane waves here and plane waves over here, and then there's something that happens in the middle that shakes the system up, where I don't know how to write my waves anymore, I just propagate them through the equation and then look at what happens. Okay? But I don't have that anymore. What's happened? If I go and take that away and use sort of the more modern way of thinking of Hawking radiation, where I have this static eternal black hole, how can I marry this sort of picture together with this idea of a time variation? Okay, this thing is static. Where's the time difference? What's going on? Okay, so modulus the Hawking rate. So let's neglect, and this is what Hawking also does, and what most people always do, is they neglect what is called back reaction. Okay, so you're assuming that you have that your mass is so large. I mean, we're talking maybe billions of solar masses here, and you're emitting a photon every nothing essentially. So you can neglect sort of the back reaction, the fact that it's losing mass. And now let's re-ask. So it's a good point, but let's just for the moment neglect the back reaction and just assume that there is no change on the black hole itself, because that's not. I mean, that's not going to lead you to the answer anyway, right? Because you're saying, oh, a photon comes out and therefore it's changed in time. But sure, but it's actually I'm asking how it's the other way around that it should be working. The thing needs to change in time in order to get the photon. So we're talking about two different time variations. So even if I don't neglect that effect, I'm still not providing an answer to where is the time variation, or this time, where is the time dependence in this static black hole? Any ideas? And the clue is in the wording where, is it a sentence? Anyway, it's not important where it is, but the clue is in asymptotic. It's in the asymptotic states. What's different between something that lives at plus infinity, so very far away from the black hole, and something which is, here's my drawing of my hole. So let's say the event horizon is sort of here. So what's the difference between something, an observer over here, and someone over here? It's no. Sure, but still that's not giving me the time dependence that I need. I mean, let's just fix our ideas. Let's assume a black hole for a moment. Let's just say it's just outside the event horizon, or close to the event. It doesn't have to be inside, outside. Let's say it's just outside to keep things simple. So what's the difference between an observer who's here and an observer who's over here? Time dilation, yes. They measure different times, okay? So a clock over here is very different from a clock over here, okay? We know that this clock is going slower than this clock, or that doesn't really mean much. You have to be careful how you say these things because you've got coordinate time and proper time. But the point is there's a time difference between this guy and this guy, okay? So, but is that enough? I mean, that's just a time difference measured on two different clocks. Yeah, no, that's not the answer I was looking for. What he's saying there is that although the temperature might be extremely low, so you've got this 10 to the minus 9 Kelvin, so very low flux rate of photons coming out. So what he's saying is, although it might seem negligible, and probably something you can't measure, at least over a short time, he's saying, but don't forget that here we're talking about objects that could live for the age of the universe. So over these kind of time periods, then you would indeed see what you're talking about. You know, the mass of the black hole would start to reduce, and you would really start to see an evaporation. So what he's saying there is that small effects over a small time aren't really observable and don't give any change, will not change the nature of the black hole. But small effects over a very long period will lead to evaporation. Okay. So coming back to this, so I wanted to move on to other things, but this is the key. So it's time dilation. Okay, this is where the time dependence comes into play. It's still not the complete picture though, because one could argue that on Earth we have time dilation, but we certainly don't have Hawking radiation. Okay. Yes. Yes, exactly. So for example, from that so you need to fix if you want to be precise about this, you need to fix a frame. So if you fix this frame, then this watch is slowing down, and at the horizon, it will stop. Okay? I don't know if everybody's familiar with this, but this idea that, I mean, this observer, so let's assume this is what I'd call an infalling, or a freely infalling observer, and I'm at some asymptotic observer, so I'm very far away. If I look at what happens to this guy, I will actually never see him disappear through the horizon. Okay? Because from my perspective, his watch slows down and eventually stops. He's sort of frozen for eternity at the event horizon. Okay? So, but that's still not enough to sort of explain Hawking radiation. In order to do the whole calculation, you also have to, I mean, you have to include the fact that you have horizon. Okay? Because otherwise, if you don't use that ingredient, one could be led to think that you might have Hawking radiation in any scenario where you have a slowing down of time, which is not what happens. And the key feature of the horizon is that, again, if you think of sort of the physics of what's happening here, what you're looking for is a mode which is emitted from the horizon. Okay? But this mode exists, if you think of it where its interval of existence is, it exists outside the horizon, but as soon as you reach the horizon, there's sort of like a discontinuity inside the black hole. That outcoming mode, this beta, which you're trying to measure, that goes to zero. Okay? And it's this sudden discontinuity, this horizon, it's like a membrane, and it cuts off the mode. So the mode exists outside, but does not exist inside. Okay? Can't exist inside, because if it was inside, it would never get out. It would just fall in. Okay? That's the infalling mode. So you have these two modes. One falls in, he exists only inside. I'm looking at the mode that comes out. In order to be outside, he has to be completely outside. Okay? So there's sort of a sharp truncation at the horizon. And it's this sharp truncation, actually it's not too dissimilar to the mathematical analysis that's done in this paper. If you think of what happens in the Fourier domain, when you have sort of a sharp edge, it means you have a huge spectrum. And that huge spectrum will cover also the negative frequency part. Okay? So you have this mode that is highly populated. It's a very broad spectrum. It's also got negative frequencies. So then when I go and do this projection onto the alpha and beta modes at the output, I find that the beta, the negative frequency part, is different from zero. And that is where the time variation, due to this time variation, plus the presence of a horizon, sort of this is the modern derivations of the whole process, actually come into play and create Hawking. Okay? So this derivation, I think it's still a very useful paper to read. If you haven't read it, do give it a read. This original paper where he came up with the idea has been criticized for these reasons, also for other reasons, but the idea was correct. I mean, now the Hawking effect has been derived in so many different forms and shapes. I think there isn't really any doubts that the maths is correct. Okay? Which brings me on to the next topic. So I sent out another file. This is a news piece by Natalie Volkova. She's a science writer. She's got a blog on Quantum Magazine. I don't know if any of you are familiar with this. And she recently wrote a piece which is, I think, very timely and very relevant. And it's entitled, Can Analogies Reveal the Laws of Physics? So that's what I want to talk about. Let me first bring up another citation. This is from a paper that I mentioned you should try go reading. This is the Living Review paper by Barceló, Liberati, and Visser, where they had like this gigantic overview all of analog gravity. This is the very first sentence that they write. They're citing Johannes Kepler. And I cherish more than nothing else the analogies, with a capital A. Okay? My most trustworthy masters. They know all the secrets of nature. And they ought to be least neglected in geometry. So this is the essence of analog gravity in general, everything I've been talking about. You know? So let me rephrase this differently. Why is this relevant to analog? What are we doing with analog gravity? So you have the Einstein equations. Those describe the dynamics of how a mass, think of the left-hand term and the right-hand term, of how on the right-hand side you have the stress-energy tensor, which describes your mass distribution. How does that change on what you have on the left-hand side, which is essentially the curvature of space-time? And the two things interact with each other. So there's a lot of nonlinearity going. Okay, change the mass distribution, which changes the curvature, which then changes the mass distribution, and so on. They're highly nonlinear. Okay, so that's not what we're trying to reproduce here. Although tomorrow I will show an example where we're kind of going in that direction. What we're trying to, so that's what you would call the dynamics of the gravitational system. What we're trying to reproduce here is the kinematics. Okay, so you have two levels. You have sort of the Einstein equations, and then you also have another way of looking or describing sort of effects of general relativity is just by referring to the metric. Okay, and this is what I would call the kinematics. How do particles, or proparticles, or photons, for example, propagate inside a given metric? And it turns out, this was the beauty of Unruh's intuition, it turns out that, for example, Hawking radiation is a kinematic effect. You do not need the Einstein equations. He never uses the Einstein equations. Okay? He only uses metrics, and that's all you need. It's a purely geometric effect. And that's why this quotation is being pulled out here. They ought to be less neglected in geometry. And that's the essence of general relativity. Right? It's all about the geometry. I can take that geometry and I can try and study it somewhere else. If you get the geometry right, you should be able to get the physics right. And the question is that true? That's what Natalie Volkova is asking us. Is that true, and to what extent is it true? Okay. Did everybody have a chance to read this? Some people. Let's quickly go through it together, just to see what she's saying. So the first sentence, the sort of summary here, is so-called analog experiments are becoming increasingly common in physics, but do they teach or mislead? It's a very valid question because it's not just about analog gravity. Let's go down a bit. She does provide another example. So let's see. I don't want to read everything. But for example, here she's saying the quantum realm, the Big Bang physicists are experimenting on analog systems made of fluids and other materials that can be modeled by similar equations. And then results from these analog experiments often end up in top scientific journals. This piece was sort of published following up on Jeff Steinhauer's papers in Nature Physics. Okay? So he's gone to Nature Physics and said, I've measured Hawking radiation. True or false? It's a very valid question. And so she's interviewed a few philosophers here. And so under which conditions can evidence that we obtain here in a certain experiment confirm or support claims about a different system which is far away? So for example, the experiments that I showed you earlier today in optics, let's just assume for moments that they're all correct, or the Jeff Steinhauer experiments in BCs. The claim is there's Hawking radiation. What do you think that tells us about Hawking radiation from a real black hole? From an astrophysical black hole. Yes, so I agree on this very last thing you said. That's absolutely true. In these analog models, I think we also always need to be careful. What we're reproducing is the mathematics of the model. Okay, good. So is that a bad thing? Is it a good thing? So with that in mind, how far can I push the claim? What can I claim that I've demonstrated, and what can I not claim that I've demonstrated? Okay. Mm-hmm. That's another good question. So let's hold on to that for afterwards. Why are you actually doing the experiment in the first place? But continue. We'll come back to that. No, continue. Yeah. Mm-hmm. Mm-hmm. Okay. So what do you think? Mm-hmm. Mm-hmm. Yeah, I think that's a very valid point. So one could claim, this is coming back to your question, why are you doing the experiment anyway? Because you could equally just do a numerical simulation on the computer and get an answer. That's I can counter-argue against that, but there is an argument for saying let's do the experiment, because when you do the experiment, you're always going to learn something. So in a computer, you can only put in, the computer will only solve the equations that you put into the computer. So there shouldn't really be any big surprises. I mean, there might be, because the equations can be very complicated. So you don't really, by looking at Maxwell's equations, there's no way you can describe what happens, for example, on the three-slit experiment, to what we just saw earlier this afternoon. So, but the computer will only tell you what you give it. So you give it some equations, and that's all it will solve. No one tells you this, it's not written anywhere that those equations are most definitely what reproduces, that those are the equations that reproduce all of reality. So I think there's still value in doing experiments, but what are your thoughts? Mm-hmm. Yes. Yep. Yep. Yes. Yeah. Yeah. I mean, if you go back, you don't need to go back that far. If you go back to the 700s, I mean, physics was purely experimental, right? There was hardly any theory out there, and the theory that was out there wasn't fantastic. Let's go back a bit earlier, maybe early 1600s, okay? You had to try things out, and everything you understood, I mean, you go back and look what they did, so the discoveries they made, sure, it took maybe 100 years to make a discovery instead of the 2 or 3 years it takes now, because they didn't have any theory of computers, but they understood everything by experiment alone. So true, that's also a valid point. Yeah? Yeah, so what he's saying is you've got system A, and then I've got system B, and apparently the two have nothing to do with each other, but I simulate system B. This is the one that I do measurements on. What does it tell me about this guy? Okay, so the nature you're investigating is this nature. What about this one? Mm-hmm. But try to transfer that reasoning to here. I mean, there was gravity and there was gravity, right? But here I have gravity, and here I have fluids. Okay? Okay, so question. So let me ask a very straight question here. Hands up who believes, so let's just assume that Jeff Steinhauer's or Wolf's or mine, whatever, that there's an experiment out there, it's done. It's been demonstrated in the lab that a BC, for example, flowing BC, can give rise to Hawking emission. Okay, so about quantum, let me rephrase that. So quantum fluctuations are excited from the vacuum state and they become real phonons, and I can measure the entanglement. And that only happens in the presence of the analog of an eventizer. Okay, great. So the question now is, hands up, who thinks that we have now, without any doubt, demonstrated that an astrophysical black hole emits Hawking radiation? Is that you asking a question or you putting your hand up? Okay, let's just do a census though. Hands up then, who thinks that you've demonstrated? No, then we'll come to the comments, but hands up just to get an idea of where the audience is. I mean Sagittarius A star, okay? So Sagittarius A star is a black hole at the center of our galaxy. Is he emitting black hole radiation? Yes or no? Based on the fact that in BCs, we've seen that the physics works. So hands up who thinks the answer is yes. Okay, interesting, only 2 people. Okay, so everyone else thinks no, so let's collect the no's. I mean, we've heard your no. Huh? There's a degree. Okay, so then hands up who thinks, that's the third question. Who thinks that it's probable that Sagittarius A star is emitting Hawking radiation? Ah, not more hands up. Okay. 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 So, and what's the basis for you thinking then that it's probable? And what's the basis for you thinking that it's actually not demonstrated? Okay. Yeah. 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 Uh-huh. Okay. Mm-hmm. So let me give another perspective to this. So I'd say that this current status is that we know so much about our BC or flowing fluid, whatever it is, systems, that we have demonstrated. So if I was to go back and, to 74 and feed all this information to Hawking, he could probably rewrite his paper. Instead of for black holes, he could rewrite it for BC. And so, but essentially what I'm trying to say is, we know everything that we need to know about our BC, and we can claim that the physics, the amplification mechanism behind the physics of Hawking emission is replicated and is present in the BC. So Hawking radiation and BCs, tick, yes, it's true. But that's because I know enough about my system in the lab. That's the whole point of doing experiments in the lab, because I can probe it, I can test it, I can measure more. I can measure all the other properties that are often needed, okay? Do I have the same amount of information regarding black holes? Do I have a sufficiently complete picture to be certain that what I'm observing in the lab, let's put it the other way around, right? So these analogs always start from, the cosmological expansion, particle production, or an exploding black hole. It starts from the cosmological model, but let's start from the other perspective. I know it works in the lab. Now let's do the analogy the other way around. Let's say, oh look, the black hole might have the same kinematics as my BC, or my flowing fluid. Will the maths and the physical model that I've demonstrated in my lab, will it apply to a black hole? So in other words, the question is, do I know enough about the physics of the black hole to say that the same physical processes occur? Who thinks the answer is yes, and who thinks the answer is no? Is that a question or a yes? That's a question. That's a no. You don't think so? Okay. No. You can make some progress in direction, sure. But I think that at the moment, as things stand, I'd say that we certainly don't know enough about astrophysical black holes to claim that maybe all of these assumptions, if you want, I don't want to sound too strong or too critical of published work, but I'd say that if we acknowledge the fact that the Hawking emission process has been verified in the BC, we know what those settings are. Okay, we've got a box, we know exactly what the stuff inside, how it behaves. Can we transfer that physics, that same amount of knowledge, to black hole context and say that is also what's happening there? I'd say that the answer at the moment is probably no. And so this is why I think I'd probably agree with people who put their hands up and said, maybe it's Hawking radiation. Yeah? Yeah? Right. That's exactly the situation. Right. I agree. Yeah. I fully agree. Yeah. Mm-hmm. Mm-hmm. Yep. Mm-hmm. Yes. It's a good question. So actually, I think, there you go. Is that because you're inspired by what she's saying there? So one of the other, so this brings us nicely to here. So she's not only, Natalie is not only talking about black holes here. So in the literature at the moment, if you go out there, so the last, I'd say 6 years roughly, okay? If you look at how the publications in these analog models been increasing, it's not being an exponential increase. Okay? People are doing analog models all over the place there. People are using, we were talking yesterday evening about people using arrayed waveguides to simulate graphene. Okay? And we are asking, why would they do that? And here Natalie is talking about, so in 2014, researchers report in Nature they discovered a particle-like state, again, in a fluid, okay, of supercooled rubidium atoms that is analogous to a magnetic monopole. So, one physicist quoted in Nature News deemed the discovery one more reason why the magnetic monopole as a fundamental particle should exist. But is it really? Sorry? Here, this part here, I don't know if you can see that far, okay? So essentially there's a group that was, by looking at a superfluid, they claimed that they'd seen a behavior similar to a magnetic monopole. It's behaving like, so you can create, so one thing that people are really working, there's a lot of work going on right now, is creating sort of these artificial gauge fields, artificial magnetic fields, okay? And I can do that even a system, I'll be showing you a system tomorrow where we are also working on this. I won't show any results of that, but using photon fluids, in this case superfluids, by putting them in rotation, you can create a current, and then you can create the analog of a magnetic field for the particles or for the excitations that live in that system. Okay? And what these people managed to find was the equivalent of a magnetic monopole in a system like this. Well, it depends what so they found the analog, they found an excitation in the material that was behaving in terms of, remember, it's an artificial magnetic field. That artificial magnetic field appeared as if it was coming, it was just a monopole. So they found that, it's been seen, it was published in Nature. So the mathematics you're talking about is a bit like what I was referring to over here. You've got dynamics and kinematics. That result is a specific result of the Maxwell equations that you saw, okay? But if you take a slightly different set of equations, or you take a system where you can slightly modify the equations, then that monopole term can actually become different from zero. Oh no, they're correct, sure. But you can have other systems where, sure, they're correct, but there might be other weird oddities, things. You know, there's always space for corrections, right? Adding things in. And essentially, this is what these people were claiming in this paper here, or rather, the physicist who was commenting that paper was saying, well, the fact that they found an analog, essentially what the physicist is saying there, that someone's done an experiment in a system that is not governed, strictly speaking, by Maxwell's equations, but it's governed by the laws of hydrodynamics. They found in that system a magnetic monopole, which is supported by the mathematics of that system. Okay, so whereas before we didn't even have a mathematical system where that monopole exists. Now we've got one, and we've seen, we can build an experiment. It's something real. Okay, and then the question is, does this really mean that maybe the magnetic monopole as a fundamental particle actually does exist? And I guess that's open for debate. I mean, here it's going the other way around, right? Before, with the Hawking radiation, so you've got a mathematical model for something which we know could probably exist, and then I'm trying to make a lab experiment to prove that. Here it's gone the other way around. I've got an analog model. Essentially, it's sort of the exercise I tried to do like 10 minutes ago. Here we've got an analog model. I've proven that the magnetic monopole exists. I've got the maths. I've got a physical system where this thing exists. So what about now so outside the system? Will the magnetic monopole exist in other environments? Mm-hmm. Mm-hmm. So you would conclude that maybe, you know, before you were a disbeliever, and now you're saying, oh, maybe. Okay, what do you think? Yes. Okay. That's so I think I would agree with the first half. I'm not sure about the second half, but I definitely agree that doing the analogs forces you to ask more questions and some questions which are relevant and pertinent to the system you're studying, and you do learn a lot more. Your thoughts? Yeah. Ah, okay. So let's move on to this question. Well, before we do, let's come back to that because that's exactly the sort of last question. We've got 13 minutes. I think it'll be more than enough. Mm-hmm. Yes. So I can't remember the I admit. I admit that I didn't actually go and read the paper. So all I can guess based on sort of the other work that's going on in the field is that in superfluids or in general in fluids, but not only, there are many systems where, for example, you can induce some angular momentum in the system. Okay? And then what you do is you go and look at how some fundamental excitations propagate in the presence of this angular, this rotation. And then when you write out the equations, if there's, just due to the interactions, you find that your fluid can be recast in the form of, as you say, a vector potential. And so that vector potential is then, this is your artificial, gives you an artificial gauge field. Was written in terms of a vector potential, sure, yes. I will answer that by saying it is whatever was needed for them to make that claim that it was monopole, essentially. So, yeah, so. So you want to have a divergence if you want a monopole, right? So think of the electrical field. The divergence is rho over epsilon 0, right? So, and they're claiming that they found something equivalent for the magnetic. Yes. Exactly. Sure. 0, exactly. Yeah. Oh. So I can look up the paper and send it to you, and then we can have a discussion about that. I don't know the details. So this wasn't Maxwell's equation, right? This was fluid dynamics. So But let's not question their results because we can't do that because we haven't read the paper. But let's just assume that it's correct and then sort of discuss what the consequences are. But let's read this last sentence here. So it comes back to the question that was raised a minute ago. So this here, Natalie is citing another philosopher, okay? And so, well, first part, I think this is the key. This is what we're doing now. The task now is for scientists to figure out how to interpret this new breed of experiment. So there's a revolution going on in the community. There's this new breed of experiments which are becoming more and more widespread, people doing analogs. What do they mean? And quoting Karen Dibol, he's saying, there's an intuition that there's something different about doing an analog simulation to doing a computer simulation, to doing a direct experiment, to doing a calculation. You've got these four things. Hawking did a calculation. I can try and do, so Hawking did a calculation. I did, or other people have done, analog experiments. So this analog simulation. But I can also do a computer simulation. Actually, it gets more complicated than that, because I can either do a computer simulation of a black hole, or I can actually do a computer simulation of my analog system. You said, Maxwell's equations are correct. Why should I even bother doing an experiment based on Maxwell's equations to simulate a black hole when all I need to do is do a numerical simulation? It'd be much cleaner, much easier. I'll get the same result, right? And then there's the direct experiment. Okay, this is where you usually end up in trouble. If I can do a direct experiment on a magnetic monopole, of course I'm not going to bother with building an analog. Or there's a question, should I bother with the analog? In most cases, I'd say probably not, but maybe in some cases you can. But the problem usually arises because you want to do a direct experiment. Think of a black hole, you can't do that. But what is the difference between, or is there a difference? What are your thoughts? So let's think, I guess it will change from case to case. But let's go back to this, there's all these analog black hole studies that I showed you earlier this morning, okay? So is there a difference between doing an analog simulation? By this, he means an experiment in the lab that's not a real black hole, but a simulated lab. Is there a difference between doing that, doing a computer simulation, or doing a calculation? Let's start from the calculation one, because I think that's easy. I do a calculation, and I tell you this is the theory. You look at the numbers, the calculation, okay, it's correct. There's no errors there, it's correct. Should I go and do an experiment? And so, okay, question. Who thinks I should go and do an experiment? Okay, good. I agree. Okay, what are the reasons for this? Yes? Mm-hmm. Yeah. Mm-hmm. But what you're saying is that the calculation isn't good enough. So let's assume, because you're saying the experiment is richer and has some parameters that maybe I can't control in the calculation. So let's say I'm really good. I'm the best theoretician in the world, and my calculation has everything in it. Okay? So now do you still need to do the experiment? Yes, good. Why? One at a time. Okay. Okay. But I would argue, yeah, up the back there. Yeah, go on. I think we're still missing the point. Yes? From a more senior member of our. Mm-hmm. Mm-hmm. Yep. This is definitely one aspect. So summarizing, the point of doing an analog experiment is because you learn something. In this case, for example, who cares about the black hole? The BC is really interesting, right? So that's where, you know, I'm excited by the BC or by the optical system or by the fluid dynamics or whatever, and I want to learn something new. And actually we did, so I didn't have time to talk about this. I don't think I'll have time tomorrow either. But in doing these experiments, someone was asking me earlier today, you were asking me earlier today, you did this, if you see Hawking radiation from an optical fiber, but there are textbooks that tell you how a pulse propagates through an optical fiber. So if I open the textbook, tell me at which page do I find the physics that describes the optical, the Maxwell equation process, that describes the Hawking radiation from your artificial black hole? Because there certainly isn't a chapter on this in my textbook. So Maxwell's equations are correct and describe everything. I only have optics. Where's the physical process that relies only on Maxwell's equations that tells me I have Hawking radiation? And actually, my answer to that question was, well, you know what? In doing this, we asked ourselves exactly that question, and we discovered something new that was not in the textbook, and that actually lies at the very basis of what a Fourier transform is. And if you want, if you're interested, I can explain to you what that new thing is that we discovered. But if not, we can just continue the discussion. So you had... Mm-hmm. Yes. Well, I don't know. I think the theoreticians would argue that if they're truly creative, they can calculate to discover something they didn't know, right? I mean, that's the whole purpose of them. But think of string theory, right? Let's assume for a moment that string theory is correct and broad, but that came out of nowhere, right? I mean, yeah, just for the sake of the argument. Yes. Yeah, I mean, my personal view is that I think ultimately it boils down to what we believe reality is, okay? So I think that's the point. It's not whether the theory is good enough, it's not whether the theoretician is good enough, or whether we know all the boundary conditions. I can put myself in a situation where I believe the theoretician is the best in the world, I've got a perfect theory, but ultimately and I think this is really a personal opinion, in much the same way that religion probably is. Now, what is the nature of reality? What am I going to declare is real? Is it Maxwell's equations, or is it my measurement in the lab? And I think that's what it boils down to, and that's what we need to think about. And I don't think there is a right or wrong, well, I believe there's a right answer, but I'm sure different people have different answers to that. Mm-hmm. Yeah. Yeah. Absolutely. And if you're trying to create a new theory, then sure, I mean, the reality ultimately has to be the test of this theory. But I mean, if we take Maxwell's equations, for example, okay, and there's thousands of millions of people around the world doing experiments based purely on the classical Maxwell's equations. I mean, does anybody really doubt? And why not just do the numerical simulation, right? Why go and do an experiment that only relies on Maxwell's equations? I think it's a valid question. I mean, they're so well known. I think that we can take them for granted. Why bother? But you could sit behind a computer and do it, right? You know, to buy yourself a big computer and just to do simulations. But also, yeah, so there's a bit of everything in there, yeah. Okay. But I agree. I mean, the ultimate test for any new theory is reality, of course, yes. Mm-hmm. I'm an experimentalist. I'm not sure I agree with that. What do the theoreticians think? Huh? Are we sure? I don't know. So think of, okay, so I've got a good example. General relativity. Einstein didn't know about anything about light curvature. He didn't know anything about time dilation. He knew nothing about this. General relativity was born out of Gedanken experiments. He sat down and thought and realized, just by doing thought experiments alone, that there's something weird. That if, there's this picture of an elevator falling and a light beam going through, the light beam would curve. Thinking, oh, that's weird, there's something wrong here. Or the tower experiment where you're sending a photon up, or so you're dropping a mass and then sending a photon back up and deconverting it back into mass, for example. And you end up with, you end up in trouble. You end up having to claim the only logical consequence of making everything work out. So, yeah, so I'll stop here and I'll leave it at that. But I think you can be creative with theory. Mm. Okay. 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 Mm-hmm. Oh, sure. 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 Mm-hmm. That was the final test, yes. Yep. I agree. And that was the final test, right? And that's what distinguished his theory from all the other theories, because his gave the right number. I agree. I partially agree. I mean, but what you're saying though is that the final confirmation, I think we all agree with this, the confirmation that the theory was correct came through a confrontation with measurements and with experiments and with reality. But how did he get there? I mean, this happened in 1915. But from 1905, in those 10 years in the middle, he wasn't comparing what he was doing against measurements. He was thinking. Huh? Ah, okay, okay. But you're not actually checking numbers. No, sure, you're confronting with reality, but he never saw that measurement, right? So this is the subtle difference. He never got in an elevator and dropped himself out of a plane and said, oh, look, the beam is bending. He never saw that, right? Otherwise, yeah, he wouldn't have got very far with his theory. So so I'm just trying to argue, I think, that the real theoretician can sit down, and of course he has to start from elements of reality, but he doesn't have to actually do an experiment and measure, by how much is the deflection, is it there, is it not there? He doesn't have to get in the lift in 3-4 and see what happens. You disagree on this, okay. Yeah? Yeah? Okay. Yep. Yeah. Well, he was trying to explain the Michelson-Morley experiment, though, right? I mean, he had Well, again, it's subtle because he knew there was a problem. But he didn't have any evidence that C was constant. So I see your point. But in a certain sense, he was starting from a known, well, I guess the experiment was stimulating the problem, but certainly didn't give him the answer. He had to find that. Again, so I think this is an example where, in a certain sense, you can sit down, you're given a problem, sure, and the problem is maybe raised by an experiment. But then how you solve that can either run through more experiments, can either run through numerical simulations, or maybe can just be a pure thought exercise. Sorry? Well, it can be a combination of all this, but not necessarily, right? So I think in the case of relativity, I'm not sure that it was a combination of all of this, at least not in the sort of development stage. So this comes back, my point though, did it really? I mean, did general relativity really come from the observation that if you're in a free fall, that you'll see something strange? Of course, of course, of course. No, sure, of course. I mean, the ultimate confrontation, the starting point and end point is always reality. Okay, I think we've overrun our time, so let's stop here, but thank you everyone. Thanks for the discussion.